Hi everyone, this is Parham. I'm going to talk about stable adaptive neural filters for teleoperation systems with uncertain delays. First, let's have a background on teleoperation systems with haptic features. As we know, teleoperation has so many applications from space discovery to underwater explorations and healthcare and many more. However, when it comes to design and development of a teleoperation system, there are some challenges and difficulties we have to consider. For example, time delays and uncertainties happening between the two sides of a teleoperation system. Every teleoperation platform is expected to provide enough transparency and fidelity to the operator so they can achieve the desired task in the remote workspace properly and effectively. In this study, we propose an adaptive filtering algorithm that can provide a smooth estimation of the reference signals that is required for a proper performance of a teleoperation system. Those filters has a set of coefficients that could be fine-tuned and learned through a teleoperation progress. The filtering algorithm can guarantee the stable performance and transparency of the teleoperation system, and also using Lyapunov-Krasovsky functional theorem, the learning algorithm does not get stuck in local minima while searching for the optimal solution. As we said, the reference signals in teleoperation systems are the main two signals, actually, the position of the teleoperator and the force feedback to the haptic device or the user interface. So the delay is a random and uncertain characteristic of the teleoperation system, but should be bounded and infinite. And at the same time, it should be growing slower than the time itself. So in other words, the rate of the delay should be slower than the rate of the time, which is quite practical in real-world applications. So we consider two filtering structures for each side of the teleoperation, one for the operator and the other one for the teleoperator. And each filter, as you see, they've got three coefficients, and these coefficients could be learned adaptively to improve the performance of the teleoperation. These filters are designed to be stably guarantee the performance while estimating the smooth reference signals F and X, which is required for the complete and proper task execution of a teleoperation. To designing an algorithm that can provide the estimation of the reference signals and also fine-tuning the coefficients of these filters, we have to consider a learning error, which is basically the same error of the system itself. So we have two main errors in a teleoperation system. One is the position error, and the other one is the force error. Also, we could design, or we could consider cost functions, as you see in the slide, but one based on the position or another one based on the force. And the one should be applied on the operator side and the other one at the teleoperator side. So our learning algorithm is based on multi-layer perceptron neural network. The weights and biases, or generally the parameters of this network, will be learned and updated through a gradient-based approach with an adaptive learning rate as well, which is shown by gamma. And the superscript or subscript I is for each filter, where L is for the number of the layers in the neural network. Also, for our learning algorithm, we considered a Lyapunov-Krasovsky functional, as you can see in the slide, which is based on the cost function and errors of each side of the teleoperation or each filter correspondingly. So the algorithm will be in a way that after a couple of iterations, it will learn the best sets of the coefficients for the filters that provides the best performance of the teleoperation, according to the cost functions we considered before, which is actually the errors that should be minimized ideally. We have implemented the algorithm and compared it in two other very similar approaches in the literature. One approach was basically, one study was using the very similar filter structure in their paper, in their study. However, their filter didn't have adaptive coefficients, by which I mean like their coefficients could not be learned, could not be adapted. So they were constant coefficients and they could not like change during the performance. So obviously adapting the coefficients could improve the performance, as we saw in the results. And the other approach was using this very similar neural network or learning algorithm However, we can see in terms of position tracking and force reflection, our algorithm worked much better. And with the implemented large delays, you can see in the figure, and also the learning of the coefficients, how they converge in a limited number of iterations. Thank you very much for watching my presentation.